So we are now going to have a talk by Jake Sorber. Jake has been working with the Insurance Institute for Business and Home Safety. Fascinating. In fact, I think this is the way science is going to start to progress into the future. Right now, a lot of science is done by going to a university and getting funding, mostly from the government. And now this is actually working with the Insurance Institute. The insurance companies are creating this research facility, which he'll tell you about, that will actually pay researchers to find answers to questions that will save them money. It's a win-win for everybody. Jake, I got to meet in the field last year when they were out collecting hail samples. How big was your team?
Ooh, at all times we had at least 9 people.
Okay, so
We
couple
had
of
some
couple vehicles, trucks, really cool stuff. They're really wonderful people. They're in town for a big consortium of Northern Illinois University and other places for what they call Ice Chip. Margot, are you involved in Ice Chip? Okay, wonderful. So we can talk about that afterward. We'll have plenty of time for Q&A. So if you're my students, take good notes, pay attention. And I'm very excited to welcome Jake Sorber.
Thank you very much for that kind introduction, Paul. How many of you before tonight have heard of IBHS? Just curious, by raise of hands. 2, 3, 4, 5. Okay, all good things, I hope. All good things. Okay, well, for those of you who haven't heard of IBHS, we are literally working at the intersection of weather and the built environment. And so, as Paul said, we're funded by our member insurance companies to do research on how to mitigate against severe weather's effects on the homes we live in and the places that we work, right? And so I want to give you a look into the work that we do on hail, and specifically how we've identified the issue, what is the issue, and then how IBHS is working to solve that issue, right? So I want to start out by looking at this map of severe hail report density over the past decade. And one thing that automatically jumps out at us is something that we call population bias in these hail reports. And you can see those hotspots co-located with areas of dense population. So you can pick out Dallas-Fort Worth, the I-35 corridor, going down into Austin and Houston, Texas. And then Denver on the Front Range of the Rockies, St. Louis in Missouri, Minneapolis, Minnesota, and even in Chicago. So you guys here have a population bias in your hail reports. And so because of biases like these in reports, we can't really use severe weather reports as a good proxy of return periods or where hailstorms occur most often, or hailstorm climatology. But what we can use this for is as sort of a simple risk map, right? Because if you think about it, the reason that there are more reports here is because there's more people. Where more people are, there are more structures. And where there are more structures, there's more stuff to damage. And speaking of hail damage, we'll go into the next slide here. And I almost don't even need to talk about this slide. It pretty much speaks for itself. So on the x-axis, we have every year going back to the year 2000. On the y-axis, we have insured losses from severe convective storms in billions. Okay, so if we look at this, we see a clear trend up and to the right. And that's great when you're talking about profit margins, not so great when you're talking about insured losses. Something else that you pick out a little more nuanced is in 2011 and 2020, we have some outliers. What happened in 2011 in the severe convective storms world? The tornado super outbreak, right? 2020, we had the Midwest derecho. And so these outliers are often driven by severe wind events. 2024, already we're up to almost $50 billion in insured losses. And we've had some severe wind events this year as well. I should also point out, because I know there's probably some questions, the purple bars here are dollars adjusted for inflation. And the gray bars are dollars at that year, USD at that year. 2023 blew the record loss year out of the water completely. Almost $60 billion in insured losses from severe convective storms, but no significant wind events to drive those losses. So what are we seeing in terms of that? So I want to break it up a little bit more into the different categories of severe convective storm. So lightning on any given year accounts for about 10% of insured loss. Wind and tornadoes combined account for about 20% of average annual loss. And we all know what's coming next, right? Hail accounts for 70% of average annual loss in the insurance industry. And on any given year, it can be between 60 and 80% of that loss number. And so 2023 was largely driven by hail, the losses in 2023, and hail was responsible for 80% of the loss last year. So almost $48 billion in insured losses. So what in the world is going on? Why can't we mitigate against hail damage? We've had this problem for 2 decades now. You saw the trend. It continues to worsen. So what's happening there? Let's break it down even further and look at the materials that are being affected here. This is a single closed claims study in 2012 that IBHS published, looking at a hail event in Dallas-Fort Worth. And you see right off the bat that roof damage accounted for 92% of those claims. And so if we consider this to be representative across the board, then roofs are clearly the main driving force behind all of these losses. And so what's wrong with our roof systems? And so at IBHS, we're asking, how can we reduce this roof damage to try to drive down that loss curve, to reduce the dollars that are going out the door from these hailstorms? And so we ask a few other questions. Does the current way that we test these products represent reality? Okay. Are there better performing shingles, both new and aged? So does one manufacturer perform their shingles to a higher standard than another manufacturer? And what about alternative roof covers? So asphalt shingles are notoriously bad, right? What about metal? It's more expensive, but is the return on investment worth it, right? And so asking these questions puts us on what we'll call the road to the IBHS Hail Impact Test Standard. And the first stop on that road is to evaluate the existing test standards that we use to test these materials. And so I want to start off by talking about one, UL 2218. This is the steel ball drop test. So if we go to the IBHS lab, this is our UL 2218 setup. It's just some PVC pipes connected to a vacuum system, and it will suck these steel balls up to a given height and drop them to simulate a hailstone kinetic energy, an impact kinetic energy. And so for the test method, this steel ball is dropped 2 consecutive times in the same spot. And if that shingle is inspected under a microscope and then bent over a mandrel and there's no crack visible, that passes as an impact rated shingle, right? If it doesn't, if there is a crack, then it does not pass. A couple things about UL 2218, I want to note 2 discrepancies with the test method. First discrepancy, it completely misses one of the most important damage modes we see in hailstorms, and that's granule loss on these shingles. And so you can see the granules covering that shingle. The purpose of those granules are to shield the asphalt mat from UV radiation to prevent it from rapid deterioration. And what we see with these hail impacts is that when a hailstone impacts the shingle, it compresses quite a bit. And there's a lot of shearing action interfacing between the hail and the shingle. And so it actually acts to scour those granules off. The steel ball does not do this. There's no compression of the steel ball upon impact, right? Another thing is the UL 2218 test is a pass-fail test. And so manufacturers can send their product out to a lab. They test it, and if it passes once, they're like, all right, you got the green check mark. You can send your product to Lowe's and Home Depot and sell it. This is great. But then when IBHS buys those products from Home Depot and Lowe's, and we test them to the UL 2218 test standard, we find that only these percentages of products pass. So I want to look at class 4 impacts, the yellow bars here. For traditional IR shingles, only 37% of those tests passed. And for polymer modified IR shingles, 53% passed, right? And so when you compare these things with a relative performance metric, you see that they're not impact rated to the point where they'll always resist these hailstone impacts, right? And so getting off the pass-fail testing into more of a relative performance of material is the way that we want to go here. And so all this to kind of set the stage and say test standards fail to predict the performance of shingles, right? And this is true across wind and fire as well, not just hail. It's arguable that asphalt shingles are the most difficult material to kind of pin down for a research problem at IBHS. And so we ask ourselves, what do we need to replicate and what do we need to understand about natural hailstones? So this is where we're actually getting into the hailstone piece, the more interesting part. So we say hailstone shapes and aerodynamics will affect the terminal velocity of these stones and therefore the kinetic energy upon impact of these stones. Other things that will affect those variables are like density and hail diameter to mass relationships, right? And then compressive strength of hail. How hard is the hailstone? A soft hailstone is going to have a different mode of damage upon impact than a hard hailstone. And so looking at these pieces is something that we need to do. So the next stop on the road to the IBHS hail impact test standard is to go out into the field and to take measurements of natural hail. And so in 2012, IBHS set out with our hail field program with the main goal of determining what properties of natural hailstones need to be measured so that we can replicate them in a lab to develop a better test standard. And so to do that, we would take a team out into the field and we'd go in behind hailstorms and we'd measure the natural characteristics of these stones with the equipment that we had on hand. And so we'd take the maximum dimension, the minimum dimension, and the intermediate dimension. We'd weigh these stones, and then we'd also take the compressive strength, okay? Now, how do you take the compressive strength of a hailstone in the field? Well, we actually built what we call a hailstone crusher. So it's just a pistol grip clamp modified with a load cell, a single axis load cell. We take this out into the field, collect that sample set of stones, do all of our caliper measurements, and then crush these. And then that load cell will tell us the force needed to crush that stone. And so this is a video I want to show you guys here. This is one of the one of the hardest stones that we've crushed in the field to date. Okay, maybe it's not going to play, but that's okay. Basically, it takes a lot of effort to crush this stone, and when it does crush it, it basically explodes, right? So this is a pretty hard stone. One thing that we know about the strength of hailstones is that the storm characteristics control their strength. Things like the microphysical growth regimes that they pass through their lifetime in the updraft, right? And so I already said compressive strength controls damage modes. So a harder stone is going to be more apt at denting a shingle or denting that roof material, whereas a soft hailstone will have a lot more compression upon impact and will really be efficient at scouring those granules off of that shingle. The interesting thing is, and work's been done here and there by interns at IBHS, looking at if we can forecast the compressive strength of hail. So if we know things like the supercooled liquid water content in the updraft, we know that that's related to the compressive strength because the rate of accretion, size of droplets, supercooled liquid water droplets, all these things control the type of growth you get on that hail, whether it's wet growth or dry growth. So wet growth would be that clear ice that you see in the hailstones, whereas dry growth is the white opaque ice, right? And so if we can forecast these variables, we can then potentially forecast compressive strength. And so this is an area of continuing research at IBHS. And then we published this work, making the hailstone crusher, right? And so this graph on the right-hand side is just showing us peak compressive force on the y-axis against diameter on the x-axis. And you do see there is a size dependence in terms of compressive force with these stones. But when you take the compressive strength, you're actually dividing that force by the cross-sectional area of the stone. And so there's not necessarily a size dependence, right? This graph was actually made to compare the field device to an Instron UTM, Universal Testing Machine, which is just a precision machine in a laboratory setting. It's often used to measure the tensile strengths of materials like metal. And basically the point of this was just to show that our field device is measuring what we think it's measuring, right? So basically calibrate it against a known instrument. And here's a snapshot of the hailstone database. So on the y-axis, we have minor axis, and on the x-axis, we have the major axis of these stones. Both are in inches. That blue line it represents a sphere, basically, where the minor and major axes are equal, okay? The color coding is mean strength, so the compressive strength of these stones. And now if you look at this, you can kind of see that the mean strength appears to be higher for smaller hailstones. And in fact, if you were to read this paper looking at compressive strength, they say that the 75th percentile and higher of compressive strength, all those stones that fell in that bin were below 3 centimeters in diameter. So it's a pretty interesting result, right? And when you look at a video that didn't play, but I kind of described what it was going to show you, that large stone took a lot of effort to crush, right? But that was only 0.7 megapascals. And these smaller stones are getting up to 2 megapascals. So what's going on with these small stones? There's a couple ideas. One is the residence time in the hail growth zone. So the longer these stones soak in the updraft in that hail growth zone, the longer they're in that cold environment, the harder they'll become.
Jay, could you just define the hail growth zone?
Absolutely. Yeah, so the hail growth zone is where embryos, so little grapple particles, snowflakes, are injected into the thunderstorm, and they travel across the updraft, and they collect super cooled liquid water, and that's how they grow into hail. And we call that region the hail growth zone. Yeah. Any questions, by the way, thus far? I've been talking for a while.
Smaller diameter stones versus larger.
Yeah.
With acceleration due to gravity. Which one? Okay, you're probably getting there. Okay, sorry. You're probably getting there, but I'm really interested. I know you're saying about the strength of these, but you're probably going to get to like which ones really cause the more damage, right?
Yeah,
I don't want
in terms of kinetic energy?
Yeah, I don't want to mess up your storyline.
Yeah, no,
Okay.
That's a great question.
You'll get there, okay.
Yeah, thanks for that. Just one more thing on compressive strength here before I go to the next slide, and we'll actually talk about kinetic energy a couple times here on out. But an idea is that the layers of these stones might play more of a role in compressive strength than anything else, in the sense that you have imperfections in these hailstone layers, right? Cracks, which might weaken them. But if you have more layers around that embryo, you might reduce the effect of an imperfection on the whole stone itself. Does that make sense? So this is just some of the ideas that we're throwing around and some of the research questions we have. The trouble with looking at the layers of hailstones and how they affect the compressive strength is that you have to cross-section the hail in order to see or quantify the layering of the hailstone. But then how do you crush it, right? So we're trying to look into that a little bit. So we also took this data set and we revitalized our kinetic energy to maximum diameter relationships and terminal velocity to maximum diameter relationships. This is published work. A paper came out in 2014 by Andy Heimsfeld and Ian Giammanco on this. And then a more in-depth study came out in 2018. But this graph on the right, on the top, is showing us kinetic energy to diameter relationships. And the two black lines, the kind of lines that bound the other data points, are the minimum and maximum kinetic energies for any given hail size. And so the reason that there's such a variance there is because these hailstones can have lobes that affect their terminal velocity. The maximum diameter can be the same for stones with different masses, right, depending on how spherical these stones are, so on and so forth. And so you have to have that range there for those kinetic energy dependencies. Okay, so we talked about characterizing the natural hailstones in the field. In 2015, we introduced 3D laser scanning into the field. And so something that you can do with 3D laser scanning is you can characterize the natural shapes of these hailstones in a way that you can't do with just three-dimensional measurements. Because three-dimensional measurements give you an ellipsoid, but these 3D laser scans give you the actual natural shape of these hailstones. And I actually want to pass something around to you guys here. I brought one of our 3D printed hailstones from the lab. This is from Coleman, Alabama. This is the state record in Coleman, Alabama. And this is printed to weight. So I'm going to start it with Paul here, and you guys can pass that around. Yeah, okay. So what can we do with these 3D printed hailstones? Well, obviously hail melts, right? So it limits our ability to study its shape without a cold room to preserve it. So by 3D scanning these stones, we can preserve them, and especially the giant hailstones, and then we can take them back to our lab and 3D print them to mass, just like this stone that I'm passing around. And then we took them to a wind tunnel in Germany and actually studied their terminal velocities and how they behave, how they would behave in a thunderstorm updraft, right? And we found that instead of tumbling end over end, a lot of them will actually spin like a helicopter rotor, right? They use those lobes like helicopter rotors, and they spin very rapidly. In addition, we can use these 3D models of hailstones to run radar backscatter calculations on these models as well to study how radar sees these complex hailstones. And so work has actually been done at Penn State with these 3D models. Yes, sir.
Do the models match the density of the original stone?
Yeah, they do. So they're printed to mass and correct volume, and so therefore they would match the density exactly. Yeah. Great question. All right. So yeah, Penn State has been doing work on looking at radar detection of these large lobe hailstones and how the radar sees these specific shapes. And this is an image from Matt Cumgen looking at the same hailstone in the same orientation, different polarizations of reflectivity. And so this hailstone on the left is horizontally polarized reflectivity, and the hailstone on the right is vertically polarized. And you can see the difference in the electromagnetic field on that hailstone just by changing the polarization. This next one is a pretty cool plot. This is actually from Matt Cumgen as well. On the x-axis, we have maximum diameter of hailstone, and on the y-axis, we have horizontally polarized reflectivity in dBz. That blackish gray bar represents the backscatter for a sphere, right? The reflectivity for a sphere of equivalent diameter. And each one of these groupings of data points represents a single 3D model of a hailstone, and each one of these groupings has 770 different points associated with them. And those 770 different points represent different angles of that hailstone. And so if you're canting that hailstone at different angles, this represents the spread of reflectivity values that you're going to see from that hailstone. And so you can consider that Coleman, Alabama hailstone falling through a thunderstorm updraft, and that radar beam is hitting that hailstone. Depending on the orientation that that hailstone is at that snapshot in time, it's going to affect how that radar beam sees that stone. And you see this dependency increase with size, right? So hailstones at 2 centimeters, relatively good agreement in that grouping. But as you get to more complex shapes, more lobiness, then if we take that green grouping, the spread is from 60 dBz all the way up to over 100 dBz. And so huge differences based off of how this hailstone is oriented. Okay, so we talked about characterization of natural hailstones in the field and 3D scanning and where that has led. But how hard do these hailstones hit? Right? So we don't have measurements of that in the field. And so in 2016, Ian Giamenco and crew developed in situ deployable impact distrometers. And this is what an impact distrometer looks like. How many of you have seen or are familiar with impact distrometers? Have seen them on Twitter? Okay, good. All right. So this is an impact distrometer. It's a relatively simple instrument when you boil it down. It's got a data acquisition unit in that silver box, and then it has an impact plate, and underneath that impact plate, you have a piezoelectric disc. What that piezo does is that as vibrations get sent through it from hailstone impacts, it induces a voltage, and that voltage is recorded and can be transferred into things like hailstone maximum dimension and kinetic energy flux as well. And so we have, this design came from a design from NASA, actually. So NASA had to develop an impact distrometer to detect hailstones during launches or leading up to launches so that they knew whether or not it was safe to put their rockets out there, because the hailstones would shred the insulation on the fuel tanks and then it would delay everything, right? Okay, so we'll take those impact astrometers out into the field. We have 24 of them now, and this is a scenario that we plan for. So you have a supercell coming from the west, a hail-producing supercell, 3 teams on a north-south road, okay? And we'll start deploying those distrometers about 20 minutes before that supercell passes the road to give us enough time to get the whole array down. We'll start out by deploying those distrometers 2 to 1.5 miles in spacing, and then as we get into areas of higher confidence where those hailstones are going to fall, then we will shrink that down to half a mile, maybe even quarter mile spacing to maximize the data that we get from the core of that hailstorm. And then as we exit out the south, we'll increase that spacing again. Ideally, the goal is to have the first distrometer and the last distrometer not see any hail, because that means that we've characterized the entire hail swath, right? And so this is what an actual impact distrometer deployment looks like. This was in 2019. I was interning with IBHS at this time. You can see me right here taking way too long to set up an impact distrometer. Here's the target storm in the background, and as it's coming over, obviously, it's going to be dropping hail on that distrometer, and that's going to be recording things like concentration, maximum size, so on and so forth. As we come back through and pick up these distrometers, that is when we will stop and do any manual hail measurements if there's any hail on the ground, right? I will say, I think I took so long to set up that impact distrometer because I had it set up originally, and then Ian was like, no, you need to get it above the corn. So I had to like lift it up, and that took longer than expected. So anyway, that's neither here nor there. All right, so if you are an impact astrometer, this is what you would see. And I want you to focus on the blue trace here. This blue trace, you're seeing small concentrations of subsevere hail. You can see the maximum estimated size on the y-axis. And then the red trace, all of a sudden, boom, you have large concentrations of severe hail. And then in the green, it's kind of confused. You know, it's in between. You have higher concentrations of subsevere hail here and there, and then sporadic severe hail scattered throughout. And really the reason I'm showing you this plot is to show you the variation over one hail swath. All 3 of these distrometers were deployed within 2 miles of one another. And so you can see how much that hail concentration and the hail size varies over that 2 miles in this swath. This is kind of a look at it spatially. This particular event, we had a tornado spawn, and we actually got to deploy on the same storm twice. So on the left-hand side at 2313 UTC, we deployed on this storm. And then on the right-hand side of that plot, we deployed again at 104 UTC. And I want you to look at the size distribution of the maximum detected hail size at these distrometer locations. So each blue dot is a distrometer location, and the maximum estimated hail size at each distrometer location is about what we would expect. So the larger hailstones are generally going to fall out closer to the updraft. Because they're larger, they have higher terminal velocities. They can't be sustained within the updraft for as long. And then those smaller hailstones are going to be lofted away, and therefore they're going to be further from the mesocyclone, from the updraft of that thunderstorm. And we see this consistently in our field data. Okay. Now, to kind of summarize 12 years of field work in one slide, if we can even do that, we've cataloged 93 thunderstorm events, 4,683 hailstones. We've 3D scanned 235 hailstones, 4 of which were U.S. state records in Alabama. That red one that I just passed around, that's the Alabama state record. Texas and Colorado. Fun fact, the Texas state record was just broken officially a few weeks ago. An almost 7-inch hailstone was evaluated using machine vision. This is the first time, to my knowledge, that the National Weather Service has accepted a machine vision analysis for a state record hailstone. It beat the previous record, which was 6.4 inches from Hondo, Texas. So pretty impressive. Okay, so we have all of this information about natural hail. We've taken over 4,000 measurements of natural hailstones in the field. We have 3D scan data. We have impact astrometer data. So we have information on their kinetic energy. Now what do we do with all that? It's one thing to know what to do. It's another thing to actually be able to do it, right? So the next two stops on the road to the IBHS hail impact test standard is manufacturing the laboratory hail and then developing a new testing protocol that's actually representative of this hazard. And so how do you manufacture hail in a lab? Well, the obvious answer is you go and you make a hail machine, right? And so this is the hail machine that we developed at IBHS. And essentially, it carbonates water, so we can control the gas diffusion pressure and duration, the freeze temperature and duration, and the thaw temperature and time. So we'll diffuse carbon dioxide into water at a given pressure, and then freeze that for a given amount of time, and then that is extruded out of the machine as a rod. And as that rod is coming out, we have heated dies that will form sections of that rod into hailstones of the desired maximum dimension, right? So here's a look at that hail machine in the IBHS lab. You can see where the PVC pipes have the black insulated material around it. That's where those ice rods get extruded from, and then the dies will form those hailstones from that rod. So for this slide, I want you guys to draw your attention to the upper left of the screen. So this image is showing the opacity of these stones, where red is white is the opaque ice, and the blue is the clear ice. And I want you guys to see that the lab hailstone almost mimics the layering structure of the natural hailstone, right? But it's for a different reason than the natural hailstones have a layering structure. So as that ice rod in the hail machine is freezing, that carbon dioxide is actually effervescing at different points during that freezing process. And so we developed this layered structure in the lab hailstone, whereas obviously we know that the natural hailstones are getting that layered structure as they pass through different microphysical regimes, right? So then as these hailstones are coming off of the machine, we test them to make sure that they're up to spec with the natural field stones that we have measured. And so the plots on the left, if you look at the top, that's the probability density of the bulk density of the hailstones, okay? So that green bell curve represents bulk densities where we would expect to see soft hail. It's between 0.6 and 0.8 grams per meter cubed. And that steel gray bell curve represents bulk densities that we would expect to see hard hail. Excuse me. And then on the bottom graph, you have compressive strength, the compressive strength distribution. It's a log normal distribution. And in general, from left to right, as you go from softer stones to harder stones, you will go from soft impacts, soft slushy impacts, to hard shatters and hard bounces. So what are these different types of impacts that we've classified at the IBHS Hail Lab? And so from left to right, you go from hard to soft stones. You have a hard bounce on the left side where it's literally what it sounds like. It's just the stone bouncing off of the material. The hard shatter, and then the soft shatter. And the soft shatter is characterized by that snow coning on the shingle with the residue left over there. And you can kind of see the lateral shearing action if you look at the way those stones explode upon impact. And that is going to be what is scouring those granules off. So at the impact site, when that hailstone compresses and shears laterally, that's going to scrub those granules off. Okay, and then we'll analyze each impact site with machine vision techniques and then rank them based off of their scores in the tearing regime, the granule loss, and the denting. And then we can put all these together in an overall rating. And the first time we did this was in 2019. And so we rated products based off of their performance to these three metrics, gave them an overall rating, and rolled this out to the public. And so in 2019, we actually had manufacturers respond, and 2021, where their product performed poor enough that they were like, we don't want our name associated with this. So they took it off of the market, right? which is good because then the consumers don't have that product on their roof, and then insurers don't have to worry about insuring that product, right? And so this is already bearing fruit as we go forth with this. So the most recent one was in 2023 that we rolled out. We do this every 2 years. But the reality is that it's not enough for IBHS to just roll this information out every 2 years because it's not going to make lasting change, right? So we need other testing labs to adopt our test standard. We need this to become a new ASTM test standard, just like UL 2218 is an ASTM test standard. And I don't think that loss curve will begin to start coming back down until we get excellent performing products into building codes. Where if you're in a hail-prone area, you are required to have an excellent performing roof cover product on your roof to potentially avoid having to replace that roof after a marginally severe or 1.5 inch hailstorm, if you will, right? Absolutely.
What do you say the cost to material to meet these? I don't know if you call them standards. Are these called standards now? Do you refer to them as standards or just something to compare to? Yeah.
So these rankings right here?
Yeah.
Yeah, so these are the impact ratings that we at IBHS put out.
Yeah,
these are not accepted standards.
Yeah, exactly.
Yeah.
But those who try to meet, manufacturers who are trying to, what is it doing the cost of material? Is it like astronomical or is it?
The difference between the costs of the excellent performers and poor performers.
What they used to put out all the time versus what, okay, I meet this now. What is that doing?
Yeah, so that's a great question. For impact-rated products, they're generally more expensive products across the board, right? Between manufacturers, I don't think the cost varies as much as it does between impact ratings. Now, if you go and start looking at composite shingles and metal roofing, well, those are quite a bit more expensive than asphalt shingles, but they're also going to perform better, right? So yeah, return on investment is a huge thing that we look at, and it's definitely a consideration. Okay, thank you. Okay, so the road ahead. What's in the future for the IBHS field deployment? So we want to start looking at, and we have started looking at, kinetic energy flux to damage severity. We want to start characterizing wind-driven hail. So obviously, hail doesn't just damage roofs, it also damages siding, right? And the performance of other building materials, like metal roofing and composite shingles and siding. And so how are we going to draw the comparison between kinetic energy flux and damage severity? Well, in 2023, we started deploying asphalt shingle panels with the distrometers in the field. The main goal of this originally was just to look at the verification, just to verify the damage that we see in the lab. But then we realized that we have a research opportunity with this, and we can actually take these panels back to the lab, assess the damage severity on them, and then compare that with the accumulated kinetic energy on the panels, right? And so this is a video, there we go. This is a video of a panel deployment. And so we have 2 panels per site, north and a south panel, and then in between those we have GoPros, right? Because we want to capture video of those hail impacts on the panel. And then obviously we have the impact distrometer that gets set up with those panels. So panels that get hail, we'll bring them back to the lab and take after photos of them, mesh those with the before photos, and then we can use machine vision and image processing to assess the anomalies between those 2 photos. And these anomalies represent granule loss on these panels. So here's a video of the worst hail exposure we saw this year. This was from 2024's deployment. The biggest hail that we had on this panel was 2¼ inches, and clearly you can see high concentrations of severe hail on the ground there. On the right-hand side is a graph showing accumulated kinetic energy for different surface areas. And so that bright orange one on the bottom, that's the accumulated kinetic energy on a distrometer. The medium orange is the accumulated kinetic energy on the panel, and then the deep red is per square meter. And then we take them back, and obviously we do the machine vision analysis. So the chart you're seeing here is granule loss for different products of asphalt shingles. The color coding represents, so the black is not deployed, panels that were not deployed. The brown or reddish color are impact rated shingles, and then the cream color is non-impact rated shingles. And so I already told you that this was the worst exposure by far that any of the panels had seen in the field. Which bar would you guys associate that with on here in terms of granule loss? Probably the largest one, right? Well, it was actually this one. And when you compare it with a panel that wasn't even deployed, it's about the same. So what are we seeing? Well, if you were to inspect this panel with your hands and eyes, there was no discernible damage on the panel. And you might say, well, you just told us how bad asphalt shingles are. I did say that. So all these panels were brand new products, brand new shingles. And what we're finding is that brand new products, whether impact rated or non-impact rated, perform pretty well, right? And so what we're seeing with this machine vision analysis, we're not even getting out of the margin of error in terms of the machine vision analysis, right? There's not even damage severe enough to get out of the margin of error. And so for the next 5 years, we're going to be looking into aged products, so aging these panels and seeing how their performance degrades over time. Okay, transitioning now to wind-driven hail, and this is where we'll finish. How often does wind-driven hail occur? Where in the storm does it occur? What's the most common storm mode that wind-driven hail happens in? What's the distribution of impact angles? This will be really important for testing siding materials at the lab, because it's not going to be at 90 degrees. It's going to have some vertical component, right? And what's the variance of those impact angles? And so in 2023, we started designing a wind-driven hail sensor, much like we did the R&D for the impact astrometer. We're working on now designing a new instrument that will be able to get force of impact data, kinetic energy data, as well as impact angle. And so this is a design for a deployable instrument. It's just a reinforced tripod with an impact sphere mounted on top of a force transducer. And so that force transducer is really the brains of the instrument, right? And so it's a 6-axis load cell. It measures forces in X, Y, and Z, and moments in X, Y, and Z as well. It has a limiting natural frequency of 2.5 kilohertz, meaning that it can sample 2,500 times per second, and it minimizes crosstalk between channels. So what does that mean? Well, if you have an impact purely in the Z-axis, it minimizes the noise that X and Y are going to see. And so it increases the quality of data collected from this instrument. Oh, pressed the wrong button. Okay. Some of the design considerations while we were building this, or designing this machine, we wanted to mount the load cell at the center of, the geometric center of the sphere. And what that does is it makes for a consistent bending moment. So at any location on that sphere, if a hailstone impacts it, it's going to have the same bending moment. And so that removes an unknown from our system of equations, right? There was an issue that we discovered. So increasingly tangential impacts on the sphere affect the ability to resolve the velocity vector from the force vector, because you're actually going to reach a slip condition. And when that hailstone slips upon impact, you're not going to resolve the velocity vector from the force vector, right? And this is going to be coefficient of friction dependent. And so you're going to have a region on that sphere, a surface area on that sphere, where you can resolve the velocity vector from the force vector. But beyond that angle of impact, you're going to enter that slip condition. And so we can actually look at things like impact location that can give us the average angle of impact and the variance of impact angle. And so this is an idealized look at what that would be like. And so consider a few hailstones all impacting at the same angle. They would impact over a surface area, a hemispherical surface area, right? And so anything that is deviant from that impact angle is going to deviate from that hemisphere. So that would be the yellow area. And so looking at the different areas or the different impact locations, we can define the average angle of impact as the zenith of that impact hemisphere, right? and then the variance of the impact angle as the area of that yellow band around that hemisphere, basically. And so this is how we can actually calculate impact angle. So consider a hailstone with velocity v that hits this impact sphere. You have a resultant line of action given by that purple vector. And then we can find the point on that line of action closest to the center of the load cell by the formula given here. R naught equals F cross M, so force cross the moment, divided by the magnitude of the force squared. And since we know the sphere radius, we can then rearrange the Pythagorean theorem, right, and find the length of the line segment between the point on the line of action closest to the origin of the load cell and the location of impact. Okay? And then we can derive the position vector that points to the location of impact by taking the negative of the unit vector of the force, multiplying it by the length of that line segment, and then just doing vector addition and adding R naught to L times that unit vector. And that's how we can get the location of impact. Okay, we did get this sensor completed by the time we went out into the field this year. The first deployment took about 3 minutes to set it up. We had a low concentration of marginally severe hail. Wasn't a great case. And unfortunately, we didn't collect any data. We had some data acquisition issues due to error handling, and so it only ran the data acquisition system for about 2 seconds, and then it would shut off. So that was a bummer. I think when we ran into Paul and company in the field, Ian and I were doing some intensive troubleshooting on the DAC to see if we can get it fixed before that day's deployment. But the ongoing troubleshooting is continuing, and we did find the culprit. So hopefully we will have this machine running, the sensor running by IceChip for next year, which, by the way, is finally funded. So IceChip is the largest hail field campaign since the 70s. We at IBHS are very excited about it, and preparations have already begun at the lab in Richburg, South Carolina for that. So with that, I'll stop talking. I've been talking for a while, and I'll accept any questions. But thank you all for your attention. Any questions? This guy's got a question too.
Go for it.
Yeah.
Hi there. Great presentation. Thank you very much. I'm curious. At the very beginning of your slide, you had a nice pie chart saying a very high percentage of the insurance loss is from hail. I'm curious how much of that hail insurance loss is agricultural?
Great question. That's all residential loss.
Ah.
Yep, so loss on residential homes. This gentleman had a question here.
Hi. So I was just wondering, you mentioned in your slides how you did field impact testing with the little roof panels you deployed in field. I just wanted to know, how did those tests compare to your lab tests? And additionally, were there any changes you made to your process in the lab based on your observations in the field?
That's a great question. Yeah, that's a really good question. So we didn't see any damage on the field panel, right? Even though we saw 2¼ inch hail in the field. One thing to think about is the maximum size of hail in the field isn't going to be equivalent in mass to the maximum size of the hail that we're using in the lab, right? And so that's a consideration that we've actually had conversations about at IBHS. And it's actually very fresh. And so we're still working through that. But we do see new products in the lab performing well to our standard. And so it's not really a surprise when we go back and look at the panel in the field that didn't show any damage, because we do see some of those impact-rated products performing well to the baseline impacts, which is brand new impacts. Yeah. Does that answer your question?
Yeah, I guess something else I just thought of. I guess this is also probably something you're in the process of figuring out, but how can you reliably
replicate old panels, like an old roof?
Okay, great question. Yeah, so we have an aging farm. So we stick panels out onto the aging farm, and we age those shingles naturally over various years.
Let them sit outside forever.
Let them sit outside. So we just harvested 10-year panels this past year. By the way, they performed very poorly to hail impacts. In fact, we would cut out the samples and you could see through the shingle. And so the material had degraded so much by that point that it was basically useless. And at that point, you get water intrusion into the home. So, yeah.
Here, while you're doing that, Jake, I have a question, kind of an educational standpoint. What is the learning curve for all of this work that your teams are doing, and who's working in the lab, who's in the field with you, what are their background experiences? And like, I'm assuming you have engineers and students and meteorologists like you are, or can you just give me a little background on how you learn all this stuff?
Yeah, that's a great question. So a lot of the people that we bring in the field have no meteorological experience at all, right? We do have engineers, and we even have a geologist on the research team. He doesn't do geology, but that's his background, right? We bring media personnel into the field, so on and so forth. A lot of the lab techs have various backgrounds as well. We just hired 2 new lab techs that have meteorological backgrounds, so we're excited to have them there as well. But yeah, does that answer your question?
I mean, yeah, and did you, like when you yourself came into the field,
Yeah.
you know, how is the learning process taking place? I mean, you say you have discussions over this. Do you just have a team that discusses things and reads papers and talks about it, or do you come in there with? I'm assuming there's no class in hail damage on shingles
No.
in college.
Honestly, a lot of it is done over. Like we'll be discussing in the break room, or it'll be an aside in a meeting, and if you know Ian Giamenko, like he gets a thought in his head and he's like the enthusiastic visionary. He's like, all right, this is what we need to do, and a lot of times we'll just design an experiment right there. So yes, we do a lot of, like, all of this is based off of peer-reviewed research, right? Like we publish papers on the research that we do at the Hail Lab. But yeah, like we do sometimes just talk about stuff just in a conversation, and that's where we do a lot of our brainstorming and get a lot of our ideas for our research. Yeah.
Yeah, Jake, thank you very much. You had a great presentation. What is the spatial and temporal limits of your operations? In other words, on January 5th, would you go out into Alabama, let's say, if there was a late season severe weather outbreak, and deploy there?
That's a good question. So the answer to that would be no, generally, because we have other responsibilities at the lab. Like we can't just do hail research all year. It would be great if we could, but we also have 3 other core perils like wind, wildfire, and wind-driven rain, right, that we look at. So generally, we have to have a set time block where we're going to go out into the field and deploy. We have looked at doing southeast deployments in the early spring. We have done that, but we can't just pick up and go on a whim for an entire deployment. What we have done is we've picked up and gone to 3D scan state record hailstones. So if somebody stores a state record hailstone in their freezer, we can go 3D scan that. Yes.
So this is the first indication I've had that there are limits to what you can do. As you've described this whole thing, there's a wide range of disciplines and people. Who's funding this, and what are the limits on the funding? Because this seems even broader than what government or universities could do.
Mm-hmm. Yeah, so we are fully funded by insurance companies. And so every year we get our budget, and we allocate that budget based off of the research that needs to be done that year. But yeah, we get all of our money from insurance companies, And every quarter, we have to present research to them to tell them what we're doing with their money, basically, to make sure they're happy. But yeah, that's a great question.
Are they happy?
Oh, they're always happy.
Hi, thanks again. And maybe I missed it, but what would you do in a case where the wind is 65 miles an hour coming like this across? Does that affect the amount of kinetic impact when it reaches your test material?
Yeah, that's a great question. That's part of what we're trying to look at with the wind-driven hail sensor. But obviously, wind-driven hail is going to be.
Yeah, I didn't notice an anemometer by your equipment.
Yeah, so we didn't have an anemometer on the sensor in that picture, but we do have an input for that on the data acquisition system.
Yeah.
We just didn't have it on in that case.
Because from high up, it may be a fast, not so fast, fast, not so fast again.
Right.
So it might be hard to say.
Yeah, it'll definitely change.
Okay.
Absolutely. Thanks for the question.
May the force be with you.
Yeah, thank you.
I have a question. Thank you for the presentation. I'm just curious. It's probably not within the scope of your research, but I kind of want to know the impact of these experiments. How do those insurance companies use this research?
Yeah, that is a great question, and a loaded question at the same time. So the insurance companies will take the scientific data that we give them, and then the ball is in their court basically with what to do. We can't tell them what to do because that's called antitrust and we'll go to jail, right? But we can tell them this is what we're finding in our work in the field. This is what we're finding in our work in the lab. The most we can do is say you should give people incentive to build stronger, build with these better materials. And so programs like IBHS Fortified, where you fortify your house against hurricane force winds, right? If you have a fortified designation, there are some states where they will give you a discount on your premium for having that fortified designation. So that's an example of an incentive to build stronger against the hazard.
Jake, we were talking earlier at dinner, and I thought maybe you could just share an idea or two. How effective is radar at determining hail size? Maybe just.
Yeah. So we can't really determine size of hail beyond 2 or 2.5 inches. And it's because of the transition between scattering regimes, partly. So you transition from Rayleigh scattering to me scattering when you get into hailstones that start approaching the wavelength of the radar, of the radiation, right? And additionally, that graph that I showed showing the difference in reflectivity and backscattered power from hailstones at different orientations, that's another facet that adds to the complication of the problem. And so it really is a difficulty that we are looking at in the radar world. I shouldn't say we, I should say researchers at universities are looking at in the radar world to try to figure out how we can identify large hailstones, giant gargantuan hailstones in these hailstorms.
So when you see a radar estimate of 4.5 or 5 inch hail, that's kind of nonsense?
Yeah, I would say that's nonsense.
Excellent. For those of you in my classes, we're going to be talking about that determining hail size, but I hope you took good notes on the vectors because we're going to be quizzed on that tomorrow. You'll be solving the equation to determine the distance. So, do we have any other questions? Couple in the front row.
Got one more for you. What kinds of outside or external data do you use or would you want to use if it were there to help you do any part of your job? The easy ones would be satellite and radar, I'm sure. But in terms of is there a specific forecasting model product that we might not know about? Or is there something that, to your knowledge, doesn't exist that you wish did?
Yeah, a good hail swath. hail swaths that accurately tell us where hail fell, because that's a huge problem in the insurance industry where
Fell, past tense, not forecast.
fell for the hail swaths, yeah. Forecasting too, because there are researchers looking into assessing kinetic energy from reflectivity values and dual pole radar variables, and if we can correlate kinetic energy flux to damage severity, and then we can nowcast kinetic energy flux in a storm, then that all of a sudden gives us some really interesting capabilities for nowcasting, and then even going back and doing forensic analysis.
Is there any special tool you use when you're looking at, we're going to deploy in this storm because of VIL density? What do you look, max DBZ? What are you looking at?
We're usually looking at things just like basic correlation coefficient, ZDR reduction, right? Just basic dual pole variables. I don't personally look at VIL when I'm deploying for a hailstorm. Why? I just don't. I don't look at VIL. I use correlation coefficient, ZDR, things like KDP. I mean, if you have high KDP in your reflectivity core, then it's probably a lot of small melting hail. KDP values above 4 per degree, I think, is the unit. But that's well known as well. So start using KDP if you don't use KDP.
Oh, how do you not have questions? I should have a question. Are the data you collected, are they publicly available, or is it more, does it belong to the insurance company? Because I know some of them hesitate to share the data.
Yeah.
But I did some research from the university, so just curious.
I think I would have to ask about that, but I'm almost sure that it is publicly, like we could share that with, because we share like 3D scan models and radar data with Penn State University, but we also have a contract with them, so I don't know what legal borders are there. But I can ask about that. Yeah, good question.
This ice chip project that Jake's in town for, Victor Gensini at NIU is one of the, he's the PI, or he's one of the co-PIs?
He's one of the PIs, yeah.
Okay, I know I've talked to him, and he will be needing undergraduate student volunteers this summer for some of the hail projects that they'll be doing. So do you know anything about what they're planning on doing, and as far as in the field stuff? Are you working with them, or?
So IBHS is separate from the NSF grant, so we're still operating under our member funding. But I know individual universities do have funding for students to join them in the field. I just don't know what that looks like per se. But I do know IBHS isn't part of the NSF funding.
But are you working with the ice chip people?
Yeah, we are. We are working with them. Yeah, so we'll be a part of the program.
Fantastic. Jake, thank you very much for coming. One more time, thank you.
Thank you all.